All right. So this is Wilbur. What shape is Wilbur making as he's flying right now?
A circle.
He's making a circle. So he's exhibiting circular motion,
Whoa.
also known as centripetal motion, which is what our next unit will be about. It's going to be a short unit because we already know Newton's laws, so all we got to do is extend it to circular motion and then we'll be good. Might not even do a test over it, probably won't. Just so we have more time to talk about the units after that, which are my favorite, work, energy, and then momentum. So yeah, travels in a circle, right? Travels in a circle. Do you think it's the wings that are making him, like, float, making him fly? No. The wings are there just to counteract air resistance. And that's it. What force do you think is causing Wilbur to move in a circle? Nice. The tension. It's the tension in the string. The fishing line. Right. Oh. All right. So circular motion, I just did that for our circular motion unit. That's what to show you what our next unit is going to be about. It's going to be about circular motion. But now I want to talk about a much larger circular-ish motion. Yeah. And so, way back in the day, mid to late 1600s, a guy named Isaac Newton was doing some stuff, and you might have heard of him before. And one of the things that he did was he discovered gravity. Because before Newton, no one knew that when you let go of an object, it would fall, right? No one knew that until Isaac Newton, right? No, wrong. No, that's not. I'm going to get to what specifically what he actually discovered that we then give him credit for discovering gravity, right? It wasn't making a discovery; it was actually connecting some other discoveries. So, one of the things that when you have the stature of like a Newton or a Einstein or a Feynman or a Hawking, like those scientists, when you're that smart, you're allowed to do what they call thought experiments. I'm using air quotes a lot today. You're allowed to do thought experiments, which means I want to do this experiment, but I literally can't because technology doesn't allow me to, so I'm just going to think real hard about it. Most scientists don't do that. Most scientists have to do real experiments to collect real data to verify their ideas. But if you have the stature of a Newton, who probably was the smartest person that's ever lived, then you can do thought experiments. You can't prove things, but you can at least come to some conclusions and then verify those conclusions based on further observations and then maybe prove something. So Newton's thought experiment was you got the planet Earth, right? Here's the planet Earth here at the bottom. And you have, on planet Earth, you have an impossibly tall mountain. I didn't put the mountain here because I don't know how to do that in this program. But imagine you have an impossibly tall mountain that rises out of the Earth's atmosphere so you can just completely neglect air resistance, right? That's the main point of that. What's that? So you got an impossibly tall mountain that rises out of the Earth's atmosphere. And on that mountain, you got a cannon that can shoot cannonballs impossibly fast, arbitrarily fast as you want. So you can go from 0 all the way up to the maximum speed, which is, what's the speed limit in the universe? Speed of light. Yeah. But we're not going to do that because then things get really weird. So, but we can shoot this cannon real fast. So here's a cannonball, and the first speed that I'm going to shoot it with is 0. I'm going to shoot that cannonball with 0 speed. And so what type of motion will happen whenever I hit play? What type of motion will the cannonball exhibit whenever I hit play? Free fall. It's going to fall straight down. Right. Notice I have the velocity vectors there too. So we get free fall. Let me slow this down like half speed. Now remember, projectiles are also in free fall, right? We learned that. From a physics point of view, if you got an object moving in a parabolic trajectory as a projectile, it's still in free fall because the only force acting on it is the downward force of gravity. But yes, this object is in free fall, as we expect. Now I'm going to start putting some velocity on it. So I'm going to give it a little bit of velocity to the left. So if you can't see, there's a little velocity vector pointing this way now. And so what kind of trajectory is this object going to follow now? What's that? Yeah, parabolic trajectory. As we expect. It's a projectile, right? Now the only thing I'm changing is the leftward velocity vector. That's it. Not changing anything else. Same starting point, same height above the earth. I'm just going to change these velocities. I'm going to change a little more. So the velocity vector is twice as big. Now it's going to go farther. But it's still pretty much a parabola, right? However, we start noticing, in this case, we start noticing something that we haven't really dealt with. What's happening to the weight force, or the gravitational force vector? It's now slanted this way because it's going to maintain direction pointing towards the center of the earth at all times. And so notice I'm actually following the curvature of the earth just a little bit here. So that vector is going to change its direction just a little bit. Now, if you are the cannonball, it's still down to you, right? It's still pointing straight down because, down to us is this direction. If you're in Japan, down is still that direction, even though they're going to be oriented very differently from us, right? What's your question?
So is that the same concept as like the force normal, where it's the opposite of like it's on a slant, force normal is perpendicular to that, so the force of gravity in terms of like the center of the earth is always going to be pointing towards the center no matter where.
Yeah, the gravitational force always points towards the center of the earth. The gravitational force on objects near the earth is going to point towards the center of the earth. All right, so I'll go a little faster here. But as you'll notice, the faster I go, so significantly faster now, the faster I go, the more I'm actually going to curve around the earth as I'm falling, and the more that weight force is going to start changing its direction, right? So the force is going to start changing direction, but then I still end up hitting the ground, creating a friction force and a normal force. But I'm still in free fall, right? I'm in free. All three of these scenarios, was the 3, 4, whatever. All of these scenarios, I've been in free fall the entire time because nothing has changed. I always have a downward force of gravity. Yes, it looks from our perspective like it's changing direction, but from the perspective of the cannonball, it's always pointing towards the center of the earth. So let's just keep going a little faster. Let's maybe go up to 6. Now we're going to go significantly. We're going to curve significantly as we go around the earth, and then we land right there. Right about there. So if the earth was flat, we would have hit the ground like right here, right? Or maybe like right here. But because the earth is actually curved, it falls a much farther distance. And if you're the cannonball, you see the earth curving away underneath you as you fall towards it, right? As you're falling towards it, because you're moving horizontally so fast, you see that the earth's surface start to curve away underneath you, and so you travel a much farther distance than you would if the earth was flat. That makes sense? Maybe some of you are getting where I'm going. And remember, we're in free fall in all these scenarios. We're in free fall. Every single one of these scenarios. Let's go a little bit faster. Thank you, sir. So now we're going to go a little bit faster. And now we're going significantly faster than we were at the beginning. And as you'll see, I'll still hit the ground here, but now I think I started at the North Pole. Above the North Pole, I think I actually get to the Southern Hemisphere. Yep. Yeah, right below the Southern Hemisphere, or the equator, if this was the equatorial plane. So yeah, now it curved away significantly as I was traveling, right? Significant curvature, and so I traveled significantly farther around the Earth. And again, from the cannonball's perspective, the Earth is curving away underneath you. It's no longer a parabola. It's still what they call a conic section path, but it's not a parabola. It's a little more complicated than that. But again, free fall the entire time. I'm falling towards the Earth. I'm just moving horizontally so fast that the Earth's surface is curving away underneath me, and so I travel farther around the Earth before I actually hit the ground. But I'm constantly in a state of free fall. And so now, let's go so fast horizontally. And I'm not changing anything else. The only thing I'm changing here is the velocity, that launch velocity. I'm not changing the gravitational force. It's the same at the beginning. I'm not changing the distance from the Earth as my starting point, right? I got the same cannon on the same mountain, firing the same cannonball, just at different speeds. Every cannonball is in free fall the entire time for every single scenario here. But then if I shoot it horizontally fast enough, yes, it's falling It's falling towards the Earth, but it's moving so fast that the Earth's surface is literally curving away at the same rate that the object is falling towards it. Right? I didn't change anything else about this. All I did, remember, no air resistance. If there's air resistance, then it slows down and then it ends up falling. Falling and actually hitting the Earth. But if there's no air resistance, and this was Newton's thought experiment, if there's no air resistance, then it just keeps on. It's falling. If that's the only force here, there's only a gravitational force, and it's trying to get it to fall towards the center of the Earth. But because it's moving horizontally so fast, and because the Earth curves away and the direction of the gravitational force keeps changing, the Earth literally curves away underneath it at the same rate that it is falling towards it. And so we say this object is in orbit. That's what orbit is. And this is probably not a perfect circular orbit because all our orbits are not circles. Actually, pretty much no orbit in the universe is a perfect circle. What are they? Does anyone know? Ovals are technically an ellipse, right? All objects are in elliptical orbits. So, what do most people, I've said this in this class before, so you probably understand, but hopefully this visual tells you why, right? What do most people say when you ask why do astronauts float in space, or when they're in orbit around the Earth? Because there's zero gravity. There's no gravity, right? That is not remotely true, right? If you're in that satellite, the force of gravity on you is mg, right? You think gravity just magically shuts off once you get a little bit off of the Earth? I'm telling you, I go to the Rocky Mountains every summer, and I climb up to 14,000 feet, above 14,000 feet, and I'm telling you, gravity's still there because it's hard getting up that 14,000 feet. Gravity's still there. You got to fight it when you're climbing mountains. And really, this is exaggerated. Actual satellites and the ISS, the International Space Station, actually much closer to the Earth than this cannonball is in this simulation. So really, you just want to get as you still want to be close to the Earth, but you want to get far enough away so that you're not really encountering much air resistance. And so this is actually exaggerated, right? If you look at the Earth, the atmosphere is a thin shell in relation to the actual size of the Earth, the radius of the Earth. The atmosphere is very, very thin. And so all you got to do is get out of that atmosphere, and then you can orbit safely. All right. So why do astronauts float? Really?
Because they experience less gravity.
Well, no, it's almost gravity in orbit. I think it's about 9 meters per second squared. I've said the term over and over again. Why are astronauts? Why do they seem to be floating when they're in orbit?
Because they are.
It's relative
Because they are free falling at the same rate as the spacecraft, so there's no apparent weight.
Exactly. The spacecraft is in free fall, so everything in it is in free fall. Imagine this. Hopefully you never experience it. Imagine you're in an elevator, and you're high up, and someone cuts the cable, and the elevator starts to fall. What do you do inside that elevator? You float, right? You start floating in the elevator before you, unfortunately, leave this world. But yeah, you imagine cut out all sound, all friction, all rumblings in that elevator, like cut out all sensation. Just understand that the elevator is in free fall. You're floating inside of that elevator. I used to think when I was a kid, like if that ever happened to me, this is one of those weird, stupid things that little kids think. If I was in a falling elevator, all I would do is right before it hit the ground, I would just jump. And then I would jump, and I'd be off the ground, and then I'd just land like I would if I normally jumped, right? No, you can't jump because you're literally floating. You are apparently weightless because you're in free fall. Remember, your weight, your sensation of your weight is your apparent weight, and it is not your weight, right? If you are literally in free fall, if you go skydiving, you jump out of the plane, you still have mg, you still have weight, you still have the force of gravity on you, but you feel weightless because there's no apparent weight, but your apparent weight is actually what force? Does anyone remember? The normal force, yeah, or the force normal. Yeah, it's the force that pushes you up. That's why if you pick up some heavy weights, you feel heavier. Your weight didn't change. The only thing that changed is that you picked up some weights So the ground had to push up harder on you to keep you from accelerating downward. Just like when you're in an elevator and it starts accelerating upward, you feel heavier, your apparent weight is heavier, but that's only because the normal force has to be larger than your weight force in order to accelerate you upwards. So your apparent weight is not your weight. So astronauts are most definitely not weightless in space, but they feel apparent weightlessness because there's no normal force on them. Okay. So notice that this object is moving in a circle, right? Let's assume this is a perfectly circular orbit. And so think of the path that it makes as just a circle as it goes around the Earth. What is the direction of the net force in relation to that circular path? Just make the observation. Perpendicular. Where does it point towards? It's perpendicular to the path, always, and it points towards the center of the circle. And so forces that cause circular motion get a special name. They get the name centripetal force. Center, centri, or whatever, however you say it in Latin, means center. And then petere, P-E-T-E-R-E, is the Latin root for seeking, like to seek. And so center seeking force. So this object has a centripetal force on it, meaning it has a force on it that is seeking the center or pointing towards the center of the circle that it's moving in. But that force is what's responsible for this motion, right? It's responsible for that circular motion, hence Newton's actual discovery. That the force that causes objects to fall, which we've known since the dawn of mankind, the force that causes that to happen is the same force that causes the moon to go around the Earth, or the Earth to go around the sun, or any of the other planets to go around the sun, right? So that's what Newton does. The apple fell on his head, and he realized, oh, there's something called gravity. No, it's the connection that he made between orbital motion, because we take it for granted now because you learned from elementary school, gravity keeps things in orbit, right? In the 1600s, they didn't know that. Before Newton, they didn't know that. They saw that big thing out the moon, and they're like, yeah, it goes around the Earth. We can work out the geometry and stuff like that, but we don't know why. It took the development of Newton's laws to explain that motion. And it's actually this problem that Newton was working on when he invented calculus. Because to truly answer this question, you got to set up what's called a differential equation, whose solution is actually the shape. The solution actually shows you that the answer is the shape of an ellipse, right? You actually get a function that's the function that describes the shape of an ellipse when you solve that equation in that way. And so that's how we know. We knew orbits were ellipses, but Newton was able to figure it out. If you ever learned about Kepler's laws of planetary motion, he just, based on pure observation and then pretty high amount of brain power, he worked out his laws of planetary motion. He didn't know why they were what they were, but then Newton came along, made this connection, invented calculus, and ended up explaining them all. Okay, so it's good stuff, good stuff. So it's that connection. It's the connection that Newton made between the two things. And so Newton's second law, let me ask you this. What direction do you think what can I say about the law? Is this object accelerating? That's what I'm trying to say. Is the object accelerating? Let's say the speed is the same. The speed is the same. Speed's not changing. It's going in uniform circular motion, meaning perfectly circular orbit. The speed wouldn't change. So you guys say that there's no acceleration.
Is there acceleration? Wait, this is messing me up. So like gravity, the force of gravity is normally acceleration, and I don't know like that's what we do, but it's not changing. So
What's not changing?
like it's just constant velocity in a circle.
Not constant velocity, constant speed. Remember, you only have the acceleration g if you're in free fall, like without.
But the velocity.
We'll actually, I don't want to get too far ahead, but we'll actually address that when we come back after the break. So you're very, very valid concerns.
The velocity isn't changing magnitude, but it's quote unquote changing direction.
Is that what you're gonna say, Ryan?
But
It's not quote unquote. It's literally changing direction constantly.
Right, but if you make like how we do an Atwood machine where we make our coordinate system point from right.
But if you want to track, this is a good point. But if you want to track this guy's motion as he moves around the Earth,
Right.
you got to use the same coordinate system. You
Yeah.
can't constantly be changing your coordinate system because that would just be silly. That's a silly remark, but yeah, you can't. If you want to have this coordinate system, then you got to keep it the same. If you're constantly changing it, then you're really not doing much, right? Because you have no reference. You're not keeping a common reference. So
yes, it is accelerating.
So yes, it is accelerating because the velocity is changing. Velocity, this is one of the big things that tells you that vectors are super important. You can't just, I'll just use a number and not even worry about it. No, the vectors are super important. Vectors require magnitude and direction. If either one of those changes, then, and we're talking about a velocity vector, then you necessarily have an acceleration. Okay, even if the direction, even if the speed doesn't change. And I'll prove that the direction of that acceleration is in the same direction as the net force. Well, I won't do that today, but when we come back, I'll show you. All you have to do is do some simple vector subtraction. Final velocity minus initial velocity. You do that vector subtraction, tip to tail, and you find that the acceleration vector points literally towards the center of the circle, just like the force. Notice there's no force opposing the gravitational force, right? That's the only force here. If there's only one force, the net force cannot be zero. The net force, or you only get zero acceleration when the net force is zero. Right? This is another reason that even if it's moving at the same speed, because it's changing direction, it requires a force. What happens if I turn the Earth off? What happens if I delete the Earth? It then moves off in a straight line according to Newton's first law, right? So it actually requires that force. If it requires a force, a non-zero net force, then you necessarily have an acceleration. And this is a good time to introduce this concept. We can indicate that variables are forces, or are vectors, by putting a little arrow symbol over them. And we have an equation. The equation means that this side's magnitude must equal this side's magnitude. That's what the equal sign is for. But it also implies, if this is a vector equation, that the vector on this side has to point in the same direction as the vector on this side. So the force, which we know, just based on looking at it, points towards the center of the circle, the acceleration must also point towards the center of the circle. And then when we come back on the Monday we come back, I'll show you that. I'll do the vector subtraction up here and show you that, yeah, final velocity minus initial velocity, the vector I get when I do that, points it towards the center of the circle. Okay? It's tricky stuff, tricky stuff. But now you know something that 99% of people in the world, probably maybe even more, don't. Right? You take any random person on the street, you say, why do astronauts float? And they'll say, because there's no gravity in space. Most of them, the vast majority of them. Now you're one of the few, and some of you will forget, but try not to, because then someone asks you that, you're like, well, they're in free fall all the time, and then they won't believe you, and then you'll have to try to explain it. And so this program makes it a lot easier to explain it because it gives you the visual, right? Because the only thing I changed, and it's still going too, right? I haven't done anything to it since I gave it that. They just shot that cannonball at that speed at the beginning. I haven't done anything else to it, and it's still going. It's still falling. The Earth is falling towards the sun and has been for 4.5 billion years. But as it falls towards the sun's surface curves way underneath it. It's hard to conceptualize that one because the distances between the two objects are so great, but it's literally the same thing. The only difference is that you got the sun and the Earth, and a much larger distance in between them than there is between the Earth and satellites. Okay. The moon's been falling towards the Earth for about 4.5 billion years, and it still hasn't hit us. Do you think that if you were in the spaceship and you could stand on the outside with a baseball, you could throw it and hit the Earth?
Yeah.
You think so?
Because there's no way that you can throw it fast enough for it to orbit. So it has to.
Oh, it's already in orbit. It's in orbit with you.
You only have to throw it, you have to take it a small amount of velocity that it has to be able to move towards it. So it decay very slowly, but it'll still be enough.
Well, not if there's no air resistance. Watch. Let's say that this will then become a baseball.
Throw it the opposite direction that
I'm going to give it a velocity in the y direction. Now remember, just so you know, for satellites, this velocity has to be 18,000 miles an hour. Low Earth orbit is about 18,000 miles an hour, right? So that means any velocity that you can throw a baseball with is going to be not remotely close to that. The fastest pitch in the world, I think, was like 105 miles an hour or something like that. Any baseball players in here? I think it's like 105. So the velocity that you can put on it would be much less. Much less. And so let's say that this is the velocity now. I gave it a very small y direction velocity, and I hit play, and pretty much nothing changes. What you would actually see if you took a baseball and you threw it straight down from the perspective of the satellite, orbiting satellite, it would end up going down, but then it would be in an elliptical orbit. And so it would end up going above you as you went over here, and it would be... Think about this. If you wanted to go straight down towards the Earth, you'd have to throw it in the opposite direction at 18,000 miles an hour, right? Yeah. Ryan's got it.
You go straight down, but you want to just impact it. You have to change the depth of the baseball by a small amount.
But if we change things by a small amount here, it's not like we're not orbiting anymore. If I take this guy and I increase his speed, I'm still going to be in orbit. It's just going to be more... When I click the send into orbit button, it sends it into a circular orbit. And so if I go a little faster than that, then I'm still going to be in orbit. It's just going to be an elliptical orbit. Can you guys see that? So now it's in a large elliptical orbit. Unless you reach escape velocity, in which case it travels not in an ellipse, but in a hyperbola. And it travels in a hyperbolic shape. It's weird. All paths that objects can take in the universe are conic sections. Conic sections, if you take two cones and you line them up like this. If you take a sheet and just lay it right here, it makes a straight line. Right? That's a path that something can make through space. If you just slice it right here through the middle, it's a point. So that's an object at rest. If you slice it right across one of them, you get a circle. If you slice it across them at an angle, you get an ellipse. If you slice them vertically like this, you get a hyperbolic shape, which is like this kind of shape, where you got those asymptotes. You guys might have studied that, right? Those are all conic sections. So if it's got escape velocity, meaning it won't ever come back to the Earth, it'll follow this path. The asteroid that we discovered, Oumuamua, you guys remember that from a couple years ago? I think it might have been last year, I don't know. It's an asteroid that's extrasolar. It came from outside the solar system, and it's on its way back out because it's moving so fast. It went by the sun, but here's the sun. It came by, and now it's on its way out of the solar system. It'll never come back because it came from outside the solar system. It's moving so fast. Anyway, so our next unit is circular motion, but I like introducing it with that.